My name is Stacey. I'm from the Health and Safety Executive in the United Kingdom, and I'm going to talk about the technical developments we're conducting to try and support on-site workplace measurements using Fourier transform infrared, and why we're doing that. As my previous speakers have explained, the health risks for respirable crystalline silica, we know that is a huge issue. And besides of a workplace exposure limit, there is also a requirement to reduce exposures to proportionate to the risk until the cost becomes disproportionate. The metric that is most commonly and has the most established relationship, with risk of ill health is actually the mass concentration of a sample taken within the breathing zone of a worker. And we have HSE's own work here done in 2003 on the left-hand side, well, your right-hand side. We have risk of silicosis with a certain International Labour Organization score, and the risk associated with 15 years exposure to respirable crystalline silica in terms of mass concentration within the breathing zone on the x-axis. This is, just to refresh people's memory, perhaps this is how a monitoring is done to assess compliance with the workplace exposure limit, or more importantly, perhaps a health risk measurement that would establish, perhaps give an indication of risk to people's health. So in the workplace, the sampler is placed on the breathing zone of the individual, usually within 30 centimeters of the usually on his lapel. The samplers that are most commonly used in the United Kingdom are based on cyclone action, which means that the air containing the particles spins around a vortex. The heavier particles, the non-respirable sized particles, fall out into a grid pot at the bottom, and the very finer, smaller particles that can penetrate into the alveoli of the lung that cause the disease potentially are collected on a paper filter, which is placed inside a cassette in the sampler. And it's this paper filter that we take and measure using a technique. In this case, you can see a X-ray diffraction instrument. Now, we in the United Kingdom use a direct-on-filter method approach, which might lend itself to an instrument that is able to be taken onto site, because a direct-on aerosol filter measurement approach does not require any sample preparation, a laboratory-based preparation. So this is the current situation at the moment. We collect a sample from the workplace, we send to the laboratory, we wait for results. It can take weeks or potentially a month in order for a manager to get a result in order to inform his workers, by which time on a quarry or a mine, the geology may have changed and the individual may be put at risk when he was told he was not at risk because the proportion of crystalline silica is much higher. This same can occur. People on construction sites work with different materials daily, so the risk can change in these environments. Well, where we need to potentially be is we need to collect the sample, obtain the result at the end of the shift or the task, and provide same or almost instant feedback at the end of the day. And this is emerging possibility with the technology today, commercially available technology today. These are the laboratory-based methods that can measure mass concentration or a mass collected on an aerosol filter. We have X-ray diffraction and Raman spectroscopy. Now the metric here is directly related to both the type of crystalline silica and the crystalline structure. So it's a very specific approach of measuring crystalline silica. We have Fourier transform infrared. Now the metric here is based on vibrations, asymmetric vibrations within the crystalline structure of silicons and crystal oxygens. Now the interesting thing is that X-ray diffraction and Raman spectroscopy instruments can cost between 60 and 160,000 pounds. We have benchtop versions of X-ray diffraction now commercially available, and these potentially could be taken to a room on a large site There are portable versions of Raman spectroscopy that are available, but the cheapest and by far the most portable version, because is the FTIR, or the Fourier transform infrared instruments, and these are within the cost range of a medium-sized industry. And actually, there are versions that can actually fit onto your hand and transport, and they can be powered by batteries and potentially operated from the back of people's cars if necessary. So the challenge is to get an accurate, reasonably accurate result. That yes. So moving on, this is what there are two aspects that we need to potentially consider when taking samples at a site. And the first one is the practicality of actually physically measuring a paper filter or handling a paper filter when you're at the site. This is what the standard practice. So we collect the there's a laser beam here. We collect the paper filter from the filter cassette. We put it into a holder currently, and then we introduce it to the FTIR measurement for analysis. But however, in some cases, even in laboratory settings, you're going to get some dust losses. I mean, for some types of sample. In this case, it's a coal dust sample. What we've done is to redesign or modify a filter cassette to allow a through cassette measurement using FTIR. And that is, we have designed the holes so that it provides the same absorbance, which is what the FTIR is looking at, the absorbance of the bands, frequencies that it's measuring. Provides the same absorbance as if the cassette wasn't there. So effectively, the idea is that we place this into the machine, press the button. Now the spectra is obtained with FTIR in about a minute, which is a great advantage when working on site. It reminds me of my days when I used to work in the radiation industry. And we'd put this at the machine in the end of our shift, and it would report a value within about the same time period, and that would obviously be given to our hygienist. So one thing about changing the aerodynamics, because we're putting greater holes in these cassettes, is that they may cause something called dust cassette losses to the wall losses, which are sometimes the filter cassette become charged, and that attracts dust particles to the sides of the filter cassette. Now, if we're on site and we want to measure the filter or provide a through cassette measurement, we need as much of the dust as possible collected on the sample filter, because that would add error and reduce sensitivity. So we tested the new modified filter cassette for dust losses. What we did was we got the filter cassette after sampling, just washed it through, sonicated it, and then measure it and compare it with the total mass collected on the filter. And this is what we got. So we've got two graphs here. We've got the proportion of the aerosol on the filter cassette, and then we've got the total mass collected on the filter. This is for quartz dust. The other one is for coal dust. And in previous work reported by my colleagues, when they first designed the Simped's respirable sampler, which is what I was shown earlier, they got an average of about 5%. They said about 5% is what they quoted in the paper, and that's the average that we've achieved with the coal dust there. So compared with other types of filter cassette, dust losses are minimum. So the other thing is, if we're taking these things to a site, we're potentially going to encourage a wider range, perhaps non-expert, proficient users to perform analysis. It's important that this analysis is relatively reliable, or at least relatively accurate, because it's going to potentially report something that is indicative of a health outcome to an individual. Now, one thing about is workplace atmospheres, and they contain, as my previous colleagues explained, is they can contain other silicate minerals. They're not clean. If they just contain quartz, that would be a perfect world, but they don't. They contain a group of minerals called silicate minerals, which have silicon and oxygen bonds in approximately the same position, that can have infrared bands that are quite close to or coincident with those of crystalline silica. In the top chart scan, we have a part of the chart here. We have a scan showing the distinctive doublet that is measured for the polymorph of respirable crystalline silica known as quartz here, and it's sitting on a PVC filter. So this is what the instrument actually measures. This is one for potash, for a feldspar known as a potash feldspar, which is a mineral mostly microcrystalline mix from a British standard that we have. The other one is a soda feldspar mineral. So that's mostly of a mineral form, a silicate mineral called albite. And as you can see, these are quite common with granites and igneous rocks. And as you can see, there are coincident bands. Am I too? Oh. So I just want to demonstrate sorry, I might overrun slightly. I didn't realize it would be 30 minutes. So I just want to demonstrate the one advantage, really. The fact we've compared 5 different methods, right, of a direct from filter approach. So the first 2 are X-ray diffraction, the last 3 are FTIR methods, and the final one is a chemometric process. And these numbers on top of the methods indicate approximately 1 standard deviation of results. This is a potash feldspar, and this is a simulated granite dust mix. And when the content is more than 30% respirable crystalline silica, for example, then all these measurements are likely to achieve compliance with the European requirement EN 482, which requires that the measurement and analytical certainty is within 30%. However, most granite dusts are not, contain much less than 30%, well, 30% or less quartz. And this is the, so we're interested in granite dust because significant exposures can occur from people working with granite. And as you can see, with the other methods, compared with the optimized chemometric method, the other methods can introduce larger errors. So benefit of is when it's trained. A benefit is that it is also, like Rietveld, able to look at multi-components within the sample. And we did some work looking at coal dust, and we were able to quantify several components to provide a more comprehensive picture of an individual's exposure. So not just one thing at one time, to be more efficient at collecting data. But also, potentially, because it's a self-learning process, well, it's not a sorry, excuse me, potentially a speculative thing here, but because it's looking at these patterns and it's quantifying the magnitude with a principal component approach, it's quantifying the magnitude of the interference, it potentially can potentially become a more leading indicator exposure rather than lagging indicator exposure in the future. If samples were taken more regularly, perhaps on-site, potentially in conjunction with real time, and with perhaps some machine learning. So that's one aspect of the future. This is our one vision. Technology in this area is moving fast. There's one vision that you can use it to take the filter from inside the cassette, provide a result, interact with the chemometrics package, and to take more immediate action to reduce exposures on site. Thank you.